short name is Ilag, and I'm the founder of Bubbles and Cafe and Curious and Connected. We have two new startups focused on research in AI as well as quantum, and possibly quantum AI in the future. But currently, my current research in Curious and Connected is focused on quantum dots and spin qubits, which are the fundamental science for quantum information science, quantum systems. So let's Basically, this presentation is centered around exploring alternative materials and methods for synthesizing quantum dots that are less toxic and more sustainable. Throughout this session, we will delve into the exciting advancements in the field of quantum dots, focusing on finding eco-friendly alternatives to traditional quantum dots. So the reason I chose to present about quantum dots today is basically because my current research is focused on spin qubits, which are the basic fundamental element for any quantum system. And quantum dots are a best candidate to research on for using to develop spin qubits. So let's see what are quantum dots. Quantum dots are semiconductor nanocrystals with extraordinary optical and electronic properties. Quantum dots emit light at specific wavelengths based on their size, a unique size-dependent characteristic, highly valuable in biomedical imaging, optoelectronics, and photovoltaic applications. And they do have a unique optical and electronic properties. They do have a lot of properties, and one of them is optical and electronic. And they are size tunable, light emission, producing different colors based on size. They have excellent photo stability, maintaining brightness even under continuous illumination. They have high quantum yield, efficiently converting absorbed light into emitted light. Applications in biomedical imaging, efficient fluorescent probes for visualizing biological structures and processes, simultaneous imaging of multiple targets, enhancing diagnostic accuracy, long-term stability, ideal for real-time tracking of cellular processes. Application in optoelectronics used in light-emitting diodes and lasers. Enables vibrant and energy-efficient displays in electronic devices, enhances LED and solar cell efficiency for next-generation technologies, application in photovoltaics, broad absorption spectrum for better light harvesting in solar cells. They can be engineered to improve short separation and transport in photovoltaic devices. In summary, quantum dots offer unique properties with applications spanning from biomedical imaging to optoelectronics and photovoltaics. So this could be the best reason why we should focus on research in quantum dots and developing materials based on quantum dots. Developing spin qubits using quantum dots. And environmental and health concerns with conventional quantum dots. Cadmium-based quantum dots are widely used and because of their excellent optical properties. Extensive use raises significant environmental and health concerns. And cadmium-based quantum dots and environmental implications. Cadmium, toxic heavy metal classified as hazardous. Improper disposal releases toxic cadmium ions, threatening ecosystems and water sources. Accumulation in soil and water harms plant and animal life. And exposure leads to severe health issues, and long-term exposure linked to kidney and lung damage, classified as a human carcinogen by ISSRDC, and concerns about potential impact on human health from released cadmium-based quantum dots. Importance of developing less toxic and more sustainable alternatives. Less toxic and sustainable alternatives reduce environmental impact and ensure safety. Shifting towards greener options allow widespread adoption without compromising the environment and well-being. So here are some alternative materials for quantum dot synthesis, but there are more, and I've just listed the basic ones. But my research is focused on finding more materials that are best suitable for the quantum dots, especially for manufacturing spin qubits. Zinc as a quantum dot core, potential alternative with similar electronic properties to cadmium, exhibits tunable emission wavelengths for versatile applications, comparable optical properties suitable for eco-friendly quantum dot synthesis. Copper as the quantum dot core offers interesting electronic properties for quantum dot applications, enables engineering of precise emission wavelengths and efficient light absorption, aims for reduced toxicity while maintaining excellent optical properties. Iron as the quantum dot core, abundant and cost-effective for sustainable quantum dot synthesis, promising optical characteristics despite different electronic properties from cadmium, ongoing research to fine-tune emission properties for various applications. Yes, that is one of the focuses of the research, and exciting potential for less toxic and eco-friendly quantum dots with comparable optical performance to conventional cadmium-based quantum dots, ensuring a safer and more sustainable future. Silicon quantum dots. These are one of the top materials for spin qubits, and they're available in abundant too. They're non-toxic and tunable emission properties for optoelectronics and bioimaging. Indium phosphide quantum dots, low toxicity, composed of indium and phosphorus, tunable emission wavelengths for lasers and displays. Zinc sulfide quantum dots, less toxic, composed of zinc and sulfur, tunable optical properties for luminescent devices and imaging. Copper indium sulfide quantum dots, potential for solar cells, composed of copper, indium and sulfur, tunable band gaps for renewable energy applications. Copper zinc tin sulfide quantum dots, suitable for solar energy, composed of copper, zinc, tin, and sulfur, sustainable and cost-effective for photovoltaics. And this is one of my interests too. And perovskite quantum dots, impressive optoelectronic properties, working on lead-free alternatives, promising applications in various fields, and we do have some research with perovskite quantum dots too. Carbon dots, low toxicity, synthesized from organic resources, useful in bioimaging, sensing, and energy applications. Germanium quantum dots, non-toxic, ongoing research for practical applications. Carbon dots and germanium quantum dots they are very promising, and there is more focus on these two quantum dots too. Sustainability of alternative materials. Key advantage: exploring alternative materials for quantum dot synthesis offers sustainability, abundance, and cost effectiveness. Abundant materials like iron enable large-scale quantum dot production. Cost effectiveness make quantum dots economically viable for widespread applications. Silicon, zinc, copper, indium, sulfur, carbon, and germanium are abundant and cost effective compared to cadmium and lead. Environmental impact. Alternative materials reduce environmental impact compared to cadmium-based quantum dots. Avoiding toxic heavy metals like cadmium minimizes hazardous substance release. Sustainable sourcing and recycling options further minimize environmental footprint. Eco-friendly applications, potential for biodegradable and biocompatible quantum dots for eco-friendly applications. Green synthesis methods for quantum dots. Eco-friendly approach. Green synthesis methods utilize non-toxic and renewable materials as precursors. Green synthesis avoids hazardous substances like cadmium using non-toxic materials and renewable resources. Example, plant extracts like tea leaves acting as reducing and capping agents for quantum dot synthesis, enhancing sustainability and biocompatibility for biomedical applications. Advantages of green synthesis: reduce toxicity by avoiding hazardous substances like cadmium, lower environmental impact, preventing harmful releases, promote sustainable quantum dot production with renewable resources. Green synthesis ensures a safer, greener approach to quantum dot production, aligning with our commitment to a sustainable future. Microorganisms for quantum dot synthesis. Bacteria and fungi naturally produce quantum dots through metabolic processes, and microbial synthesis yields less toxic quantum dots of diverse sizes and shapes, utilizes renewable resources, promoting eco-friendly and sustainable production. Microorganisms offer an exciting green approach to quantum dot synthesis, unlocking potential for safer and versatile applications. I think that should be some way to test grow these quantum dots using microorganisms in the microgravity environment in the ISS, and benefits of microorganisms based quantum dot synthesis: less toxic quantum dots compared to conventional methods, utilizes renewable resources for eco-friendly production, potential for large-scale cost-effective synthesis. Microorganism based quantum dot synthesis ensures safer, sustainable and scalable quantum dot production for diverse applications. So this is one of the interest of my research too, to grow these green as well as microorganisms for quantum dot synthesis in the ISS, in the microgravity environment. And various here I've listed the various methods for quantum dot synthesis: electrochemical, solute synthesis, hydrothermal synthesis, microemulsion synthesis, laser ablation synthesis, biogenic synthesis, microwave assisted synthesis. Most of these synthesis methods could have some challenges to test in the microgravity environment in the ISS due to high temperatures and extreme conditions, but green and microorganism synthesis are like well suited for that could be suited for ISS environment. Electrochemical synthesis, the principle is to form quantum dots by electric current as electrodes, and advantages are precise control over size and shape, scalable for large scale production and electronics integration, and limitations limited to certain materials based on electrode compatibility, requires expertise in electrochemical techniques. Solute synthesis, quantum dots formed through chemical reactions in a solution. Advantages: incorporation of various dopants for tailored quantum dot properties, produces quantum dots with superior optical characteristics. Limitation: longer reaction time and challenges in precise size and shape control. Hydrothermal synthesis use synthesized under high temperature and high pressure in aqueous solution. Advantages: straightforward and eco-friendly, suitable for various quantum dot materials. Limitations: temperature and pressure requirements limit scalability and also testing in ISS, and potential for agglomeration and reduced size control. Microemulsion synthesis: quantum dots formed in a controlled microemulsion system. Advantages: uniform size and stability, fine-tuning quantum dot properties. Limitations: complex setup, requires precise control. Laser ablation synthesis: quantum dots are generated by laser ablation in a liquid medium. No chemical precursors, precise sizing and specific materials, challenges in shape control. Biogenic methods: microorganisms or plant extracts for quantum dot synthesis. Advantages: green and sustainable production, biocompatible, and requires optimization, variability. And microwave assisted synthesis, accelerated synthesis using microwave radiation, rapid reaction times, energy efficient, careful control needed, limited materials. Surface modification for biocompatible quantum dots. Importance: safe biomedical applications, reduced toxicity, compatibility with biological systems. Techniques: coating with biocompatible ligands, polymer encapsulation, silica coating. Ensures safe and effective quantum dots for biomedical research and clinical use. Downstream environment impact: consideration beyond synthesis stage for environmental responsibility. Quantum dots used in biomedical imaging may lead to accumulation in the body. Safe elimination is crucial to minimize environmental impact. Biocompatible and biodegradable quantum dots offer sustainable solutions. Applications of alternative quantum dots: again, biomedical imaging, optoelectronics, photovoltaics. Research opportunities on the ISS: studying quantum dot synthesis and investigating biocompatibility, assessing quantum dot cell interaction for safer biomedical use. This is one of the top priority of my coming research, future research. Assessing optical properties, precise optical measurements in a controlled environment. Benefits of ISS research for quantum dots. Again, as we know, like microgravity offers a unique environment with weightlessness and less gravity, and the controlled environment could enhance optical property assessment, and space conditions reveal biocompatibility and toxicity. And potential implications: greener and safer quantum dot synthesis methods, cutting edge biomedical applications, optimized quantum dot performance for space technologies. So yeah, and if you have any questions, please feel free to email me at ilac2023@gmail.com, and you can also ask me questions now.